Hey guys, in this video we're going to talk about Chapter 3, Section 1, Introduction to Quadratic Functions. So, before we get into what a quadratic function looks like graphically, we want to talk about what it looks like algebraically. So, a quadratic function has a standard form y equals a times x squared plus bx plus c, where a, b, c are numbers and a cannot be 0. Okay, so this is what a quadratic function looks like. Notice how it's different from a linear function. Remember, a linear function was of the form y equals mx plus b, where m and b were numbers and x had the highest power of 1. Here, the quadratic functions have the highest power of 2 on the variable. So we can see that right here, our highest power is 2. So that's what a quadratic function is. So some examples of what these could look like algebraically, we could have y equals 2x squared minus 5x plus 1. And just matching up what we have up here, a, b, and c. So a is the number attached to x squared, which we can see here is 2. So a is going to be 2. The number attached to x is b, that's negative 5. And finally, this last number at the end, c, is going to be positive 1. So that's one example of a quadratic function in standard form. So another name for a quadratic function is called a parabola. I'll be using these terms interchangeably. So quadratic function, parabola, quadratic function. So remember, linear functions were lines, right? Now quadratic functions are U-shaped. They look like upside down and right side up U's. A quadratic function will either have a maximum or a minimum point, so a highest or a lowest point, and we call this point the vertex. So down here I have 3 examples of quadratic functions. This first one right here is, we can see that it's U-shaped. It looks like a U, and its vertex right here is the lowest point on the graph, right? Every other point above it is going to be higher than it. So that's an example. On the other hand, we have an example right here where the vertex is the maximum point. So this is going to be the very highest point on the entire graph. We can see that any other point is going to be lower than that maximum value. And then we have a final example right here. This time the vertex is the minimum, so the lowest point on the graph. And if you look at these 3 parabolas, they all have different shapes. Some of them are really skinny, some of them are wider, and we're going to talk about what affects the shape of those graphs in just a bit. So let's do some practice putting quadratic functions in standard form, and we want to identify a, b, and c. So let's remind ourselves that standard form is y equals ax squared plus bx plus c. Okay, so our goal is to make all of these functions look like that. So let's look at number 1. We have f of x equals x minus 3 squared. And basically we're just trying to simplify this out until we get something that looks like this. Right now it doesn't though, so what we can do is when I say something is squared, I mean we're going to multiply it by itself. So 2 squared is 2 times 2, x minus 3 squared is x minus 3 times x minus 3. Now from here we can FOIL, right? So first is going to be x times x, that's x squared. Outer is going to be x times negative 3, that's negative 3x. Inner, negative 3 times x is another negative 3x. And last, negative 3 times negative 3 is a positive 9. Okay, so this is f of x equals. So I just expanded this. Then I can combine these like terms. So f of x is equal to x squared, negative 3 minus 3 is negative 6 plus 9. So this is my answer in standard form. And here, a, the number attached to x squared, is not written, but it's understood to be 1. So a is going to be 1. B is the number attached to the x, and that's going to be negative 6. And c is that constant term at the end, which in our case is positive 9. So that was number 1. I'd like you guys to try number 2. Try to pause the video and see if you can do this one. So here we have x minus 8 times x plus 6. And since we have two binomials, meaning two terms in each set of parentheses, we can FOIL. And so foiling this out, first, x times x is x squared. Outer is x times positive 6, that's positive 6x. Inner is negative 8 times x, that's negative 8x. And last is negative 8 times positive 6, which is a negative 48. Yeah, I was doubting myself for that. Okay, from here we can combine 6 and negative 8 to make negative 2. So we get y equals x squared minus 2x minus 48. And this is our function in standard form. A, once again, is going to be 1 because that's the number attached to the x squared. B is going to be negative 2, that's the number attached to x. And c, our constant term, is going to be negative 48. Okay, let's do number 3. So here, what I can do is I can use the distributive property to multiply 2x in there. I don't need to use FOIL because the 2x doesn't have a plus 1 or a minus 1 or a minus 3. It's just 2x. It's called a monomial, meaning one term. So when we have a monomial times a binomial, we use a distributive property. So 2x times x is going to be 2x squared, right? 2x times x times x is x squared. Okay? 2x times negative 5 is a negative 10x. All right, so that is our that's our function. That's going to be g of x. So that's our answer in standard form. So a, the number attached to x squared this time is 2. B is going to be the number attached to x, which is negative 10. And c is the constant term, and we don't see a constant term, so we're going to assume that it's plus 0. So c is going to be 0. And that's our answer. Let's take a look at number 4. So this kind of looks a little crazy, but we can clean it up by foiling and using the distributive property. So this, recognize that I'm going to FOIL because I have a binomial here, two terms separated by a minus sign, and I also have a binomial here. Here, and keep in mind, FOIL is just a special case of the distributive property. And then here, I'm going to use the distributive property because I have a monomial here, which is one term, and a binomial here. Okay? So let's go ahead and FOIL the top. So we have x minus 3 times, or sorry, m minus 3 is our variable. Our variable is m times m minus 4. And then I'll put this off kind of to the side, deal with that later. So let's go ahead and FOIL this. First is m times m, that's m squared. Outer is m times negative 4, that's negative 4m. Inner, negative 3 times m is a negative 3m. And last is a negative 3 times a negative 4, and that gives us a positive 12. Keep in mind we still have this plus 2m times m plus 1 to deal with. and this is equal to g of m. Okay, now I can clean this up right here. Negative 4m minus 3m, since those are like terms, that's going to give us negative 7m. And let's go ahead and distribute this 2m in there. So 2m times m is 2m squared, and 2m times positive 1 is a positive 2m. All right, let's go ahead and combine like terms. So I see this guy and this guy are like terms. 1m squared plus 2m squared is 3m squared. Oops, not m cubed, m squared. And then we have negative 7m plus 2m is going to give us a negative 5m. And then we have the plus 12 at the end. Since we can't simplify anymore, this is our answer in standard form. So a is attached to the square variable, which in this case is m instead of x. So a is going to be 3. B is going to be the number attached to the x variable, in this case m, which is going to be negative 5. And c is our constant, which in this case is 12. So that's our answer there. Okay, so these letters in standard form, A, B, and C, tell us something about what the graph looks like. Now, we're not going to talk about B today, but we are going to talk about A and C. So what does A tell us in standard form? It tells us whether the graph has, whether it's opening up or down. And if it's opening down, so if it's opening up, maybe I'll do it in yellow. If it's opening up, I like to think of that as a smiley face, right? And if it's opening down, I like to think of that as like a frowny face. Just to, think about it in an easy kind of way. So if A is negative, the parabola opens down and has a maximum, which means it has a highest point. And if A is positive, the parabola opens up and it has a minimum, which is the lowest point. If we look at the examples that we just did, we can tell without putting this into Desmos whether it opens up or down, just based on A. Now for number 1, since A is positive, this thing is going to open up. It's going to have a happy face because it's positive. It has a positive outlook on life. So this one opens up. We know it's going to look like that if we put it in Desmos. This guy is also going to open up because, again, 1 is positive. It's just strictly based on A. This guy is also going to open up. Do they all open up? Let's see. So this guy, oh, no, I didn't mean to do that. He's very positive in life. A is positive. He's smiling. Yeah, I guess these are all these are all happy faces. So here A is 3. So this guy is also going to open up. So all of these open up because A is positive in every case, and that means that they all have minimums. They all have a lowest point. Okay. So that's what A tells us, whether it opens up or down, and the letter C is going to tell us what the y-intercept is. So if we go back to our examples that we just did, we can tell what the y-intercept is because that's C. So y-intercept for number 1 is 9 because C is 9. That's where it crosses the y-axis. So we know two things. We know it's going to open up, and we know that it's going to cross the, well, actually, that wasn't a great picture. We know that it's going to cross the y-axis at 9. That's what we know. So let's go to the next one. Here, our C is negative 48. So the y-intercept is negative 48. That's where it crosses the y-axis. Here, it crosses the y-axis at y equals 0. C is 0. The y-intercept is 0. And then down here, oops. Down here, C is 12, and so the y-intercept is 12. Okay, let's do some of these examples. Determine whether A and C are positive, negative, or 0. So looking at number 1, remember A, if it's negative, it opens down, and if it's positive, it opens up. Well, this guy is frowning, right? So he is going to open down. So first of all, A is negative because it opens down. What about C? Is C positive or negative? Well, C is the y-intercept, where it crosses the y-axis. And the y-intercept is positive up here and negative down here. So C is positive. Y-intercept is positive. Okay, let's look at number 2. So number 2, first, is it opening up or down? Well, it's smiling, so it's opening up, and what that tells us is that A is positive. The y-intercept, is that positive? Well, yeah, because it crosses the y-axis in a positive place again. So the y-intercept is also positive. Okay, let's scroll down here. Okay, so here it's opening downwards, frowny face, so A is negative. Now C, it appears that it's crossing the y-axis at y equals 0, the origin. So that means that it's not going to be positive or negative, it's actually going to be 0. Okay. Let's look at this last one. So we can see that we are frowning, and so we have A is negative again. And C is our y-intercept. Now, even though we can't see it crossing the y-axis, we know what it's going to do because of these arrows that are, that quadratic functions have. It says that they can go on forever and ever and ever. So eventually, if we keep drawing this axis, it's going to cross in the negative area, right? This graph is eventually going to extend to the negative area. So that means that our y-intercept is negative. All right, so determine if the quadratic has a maximum or a minimum and determine the y-intercept. So remember that maximum or minimum depends on if it's frowning or smiling. So here we can see that A is negative. So A is negative, which means that we're frowning, which means that we have a maximum. So maybe I'll just put this as answer. We have a maximum, and the y-intercept is going to be C, which is that constant number, and that's going to be 1. That's my answer here. Let's look at number 2. So the first thing we need to do is we need to rearrange this, because in standard form, we always want the square term to come first, and then the regular x term, and then the constant at the end. So I'm going to do a little switch right here. Just rewrite it. This is going to be negative x squared, a positive 3x, and a positive 8. And when I do that, I can see that, again, I have A is negative, and so, again, I have a maximum, frowny face. And then my y-intercept is going to be 8. That's my answer here. Let's look at number 3. So again, we want to rearrange. This time the t squared is in the correct spot, our variable squared, but we want to switch these to put it in standard form. So if I rewrite this, this is 2t squared plus 6t minus 5, and my A is 2, and that's positive. So it's going to be a smiley face, which means it has a minimum. Okay, so my answer, we have a minimum, and the y-intercept is this constant term, which is negative 5 in our case. All right, let's look at this last one here. So it's opening upwards, which means that it's going to have a minimum, and that's right here. So minimum. And the y-intercept is where it crosses the y-axis, and we can see if we look closely at this graph that it's going to cross the y-axis at negative 3. So that's our y-intercept. You can write as an ordered pair. You could just say negative 3 is the y-intercept. Okay. All right, so we just talked about standard form. A quadratic function can look a little bit different, and it can be in something called vertex form. So depending on what you're trying to figure out, vertex form, standard form, and then we're going to talk about factored form can all be useful for different things. So I want to talk about vertex form next. Now vertex form looks like this, okay? And I should mention here that A is, well, actually, we can just say A, H, and K are numbers in this formula that we have here. So here is vertex form, and A tells us the same thing that A told us in standard form. It says if A is negative, it opens down. If it's positive, it opens up. The A also has to do with how fat or skinny the parabola is, but we're not going to cover that quite yet. But for now, just know that if it's positive, it opens up. If it's negative, it opens down. Now, another cool thing that vertex form tells us is the vertex, or the actual max or minimum point. And that is going to be an ordered pair. It's going to be the h value, and it's going to be the k value, h comma k. So in our picture here that we have, we can see that this guy, first of all, this is our equation. We can see that a equals 2, which is positive, hence it opens up, it's smiling. And the other thing we can see is that the vertex, this guy is our h, the 3 is our h, and the minus isn't included because the minus is already in the formula, all right? So the vertex here is going to be h, which is 3, and k, which is this constant number at the end, as we can compare it to this formula, is 1. So this is h comma k, and we can see from the picture that that is our minimum. That's our vertex. So the vertex is either the minimum or the maximum. And the vertex is cool because it cuts the quadratic in half. It cuts it into 2 equal pieces. So if there's a line that goes through the vertex, imagine this. Imagine that there's a line that cuts the vertex right down the middle. We call this a line of symmetry because the left side of the parabola and the right side of the parabola are exactly the same portion. It's the same size. So that's what that line does for us. And what's cool about it is that, you know, if we know what this point is, this point right here is, you know, if we were plotting this point right here is 4, 3. And I know that, you know, we're going to have another point the same exact distance on the other side of that line of symmetry. All right, and we're going to put this into practice in the next slide. So it says determine whether the quadratic opens up or down, determine the vertex, determine the y-intercept, sketch a graph. So the vertex form is y equals a times x minus h squared plus k. And in standard form, we have y equals ax squared plus bx plus c. We know that h comma k is the vertex. We know that if a is negative, we have it opening down. If a is positive, we have it opening up. And what else did we need to know? Oh, and the y-intercept is c from standard form. All right. So that's what we need to do here. First of all, does the parabola here open up or down? Well, this is in vertex form. We're comparing it to this guy right here. We can see that -2 is in the spot of A. We can see that 4 is in the spot of H, and we can see that -5 is in the spot of K. So this guy is in vertex form, and we said that if A is positive, it opens up, but if A is negative, it opens down. A, in this case, is negative, so it opens down. A is -2. Maybe I'll do this in orange. So it looks like this. The next thing is to determine the vertex. So standard form isn't going to give us that, but vertex form is, because vertex form is h comma k. Now here we just said, well, -4 is h and -5 is k. They're in the same position as they are in this general form here. So our vertex is h comma k. That's our vertex. The y-intercept can be found with the standard formula. The y-intercept is c. So c, we have to, it might be -5, but it's probably not, because we have to expand this out first. We have to actually get it in standard form first in order to figure out what the y-intercept is. Another trick that we could use, the y-intercept by definition happens when x is 0. The y-intercept happens when x is 0, so if I plug in 0 for x, I'm going to get out a y value. Let's try it that way first. So the y-intercept occurs when x equals 0. So what we have here is y equals -2 times 0 minus 4 squared minus 5. And we can simplify this out, okay? So -4 squared, I'm doing order of operations, so I'm doing parentheses first and then exponents. So -4 squared is going to be a positive 16. And we end up getting -2 times 16 is -32, minus 5 is -37. So we know that our y-intercept is -37. We could also have figured this out by expanding this thing and putting it in standard form. And I'm going to do it that way, but I'm going to do it the easier way for the rest of them. I just want to show you. So if I expand this thing out, x minus 4 squared is x minus 4 times x minus 4. And then we still have that minus 5. So I'm expanding this out with the hopes of making it look like this, so I can see what c is. Now what I'm going to do is I'm going to kind of ignore this -2 for now and just FOIL the x minus 4 times x minus 4. So first, x times x is x squared. Outer, x times -4 is -4x. Inner, again, is -4 times x, -4x. And last but not least is -4 times -4, which is positive 16. Keep in mind this is all still multiplied by -2, and there's still a minus 5 at the end. Combining like terms on the inside, I get -8x. These guys make a -8x. And then from here, I can distribute the -2 in there to everybody. Negative 2 times x squared is negative 2x squared. Negative 2 times negative 8x is positive 16x. And negative 2 times positive 16 is negative 32. I still have the minus 5 at the end, so I can combine these to make what I got, which was negative 37. So this guy is officially in standard form with A, negative 2, B, 16, and C, negative 37, which does agree with our previous math. But that was a lot of work, so I'm not going to do that for the rest. I just wanted to show you that we can get the y-intercept from standard form. Okay. So let's look at the, oh wait, so it says sketch the graph. So what we can do is we can just, whenever I do sketches of graphs, I mean, they're really rough. Like, they're not the best, but they'll do. What you want to do, if you have the vertex, plot the vertex first. So the vertex in our case is 4, negative 5. So when x is 4, y is negative 5. 1, 2, 3, 4, 5. So if I go over 4, down 5, I'm right here. I know it opens down. So, you know, I'm going to have this line of symmetry here through the vertex. And what I want to do is kind of figure out a point to either the left of the vertex or the right of the vertex. This point right here, we just said the vertex was 4, negative 5. And I know it's going to look something like this. I know that it's going to look like that, but I want to actually get the points. So what I'm going to do is I'm going to hop over to x equals 5. And I'm going to plug in, I'm going to make a little rough t-chart. I'm going to plug in x equals 5 because that's to the right of x equals 4. So it's going to be, you know, somewhere over here. I'm going to see what that y value is by just plugging x into the function. This is a function. I put in the x, I get out a y. So, of course, I didn't give myself enough room here. Let's do it over here. So if I choose x equals 5, plug it in to this function, I get negative 2 times 5 minus 4 squared minus 5. And I can simplify that out. 5 minus 4 is 1, so I get negative 2 times 1 squared minus 5. And 1 squared is 1. Negative 2 times 1 is negative 2. Negative 2 minus 5 is negative 7. So when x is 5, y is negative 7. And I can just do a really rough sketch here and just say, hey, that's 5, negative 7. And what's cool is that I can just, you know, reflect this across and make another point right here, right? So this, you know, this was 1 away from 4, so this is going to be 1 away in the other direction. So 4 minus 1 is 3, and it's going to be at the same height, which is negative 7. And then you just connect the dots, and you get this beautiful picture. I'm being a little bit sarcastic here because my art skills aren't the best, but that, so you can, you know, you could do that little reflection trick that I just did, or if you wanted to, you could just say, well, let me find the other point. I'm going to plug in x equals 3 into the function for x, and then get out the y value. You're going to end up getting negative 7. But anyway, that's how you do that. So that's a little sketch of the graph there. Let's go ahead and look at number 2. So this is in vertex form. We have a is 1/3. That is a positive number, so we know it opens up. Our vertex is going to be negative 1, 3. And the reason is because this positive one, in order, if we were to plug in the h is negative 1 into the base formula, we would end up getting double negatives making a positive. So that's why the original h is negative 1. Hopefully that makes sense. If it doesn't, you can always think, well, h is the opposite of what we see. So this is our vertex, which is h comma k. And our y-intercept, I'm going to do this the easy way. And actually, I'm going to erase this graph over here just so we have some more room to work with. I'm going to do this the easy way. Remember that the y-intercept occurs when x is 0. So if I plug in 0 into my function for x, I get this. So I'm just replacing 0 in for x. And then I can simplify. So 0 plus 1 is 1. 1 squared is 1. 1/3 times 1 is 1/3, plus 3 as a fraction is 10/3. Okay, so this is my y-intercept. All right. Then I can sketch a quick graph. Again, this is rough. So let's sketch a quick graph here. And the first thing I'm going to plot is my vertex at x equals -1, y equals 3. That's h comma k. So this is my vertex. We know that this thing's going to open up. So this is -1 comma 3. This is x is -1. So if I want to get another point, I can look to the left of x equals -1, which is x equals -2, and plug that into a little t-chart. So when x is -2, I get 1/3 times -2 plus 1 squared plus 3. So this is y equals this. And again, I'm just plugging in -2 in for x because I saw it was to the left of the vertex, and I'm seeing what I get out for y. So -2 plus 1 is -1. We get y equals 1/3 times -1 squared plus 3. -1 squared is +1. So 1/3 times 1 plus 3. And we end up getting, let's see. We end up getting, did I do this correctly? I don't think I did, because we're getting 10/3 right there, which doesn't give us the U shape. So I think I did something wrong. Let's backpedal to the, let's see, -2. Okay, let's see. So when x is -1, y is 3, that checks out. When x is -2, oh, I see, y is 10 over 3, which is also the y-intercept. Okay, sorry, that makes sense. I just had to do a little backpedaling there. Great, okay, so when x is -2, when we plugged -2 into the function, we got y is 10 over 3. So maybe something like this. So this is -2, 10 over 3. And the y-intercept is to the right of -1. And that's also going to be at 10 over 3. So we kind of just reflected it over, and we can connect the dots to make that beautiful picture. Remember, the vertex here is our line of symmetry goes through it, so that's how I reflected this point over there. So yeah, that's our sketch. Let's do the next one. Erase this so we have some room. Alright, so here is our function y equals 6 times x minus 8 squared plus 1. This is indeed in vertex form. So we can see first of all that A is 6, and that's positive, so we know that it opens up. So that's our first thing. And the vertex is going to be 8, 1, because that's in our place for vertex form. So our vertex is 8, 1. And our y-intercept, so our y-intercept occurs when x is 0, so we have 6 times 0 minus 8 squared plus 1. And if I simplify, this guy is going to be negative 8. Negative 8 squared is positive 64. And so let's put this in the calculator. 6 times 64 plus 1 is going to be 385. So when x is 0, y is 385, which is exactly the definition of a y-intercept. All right. Now, I'm not going to sketch this just to save some time, but you should try it and confirm your answer with Desmos. You can always plug this stuff into Desmos and see if your picture is looking good. Let's go ahead and look at this next one. So, does it open up or down? Well, we can see this thing is in vertex form, and this is our A. So since A is negative, it's going to open down. The vertex is going to be h, k. Remember, opposite of what you see for h. So opposite of what we see is negative 5, and k is just negative 9. So this is our vertex. And our y-intercept, we have to do some math. So y-intercept occurs when x is 0. Plugging in 0 for x. We get negative 3 times 5 squared minus 9. So y equals negative 3 times 25 minus 9. And we get negative 84. So that's that. Again, I'm not going to graph this one, but you should try it out on your own and confirm with Desmos. Okay. All right, the last form that we're going to talk about is something called factored form. So a quadratic is in factored form if it can be written like this. So in this case, A, R, and S are numbers, once again. So A, again, is going to tell us if it opens up or down based on whether it's positive or negative. R is going to be a 0, and what that means is where the graph crosses the x-axis. And S is going to be another 0, where the graph crosses the x-axis. Now, it could be that your graph never crosses the x-axis, and that means that you're not going to have any real zeros. It could also cross the x-axis only once, or touch the x-axis only once, and in that case, it's only going to have one real 0. So let's look at this example right here. We have a function in factored form. Here, A is going to be negative 2, because that's the number in the very front. Our R is going to be negative 1, because again, it's the opposite of what you see because our base form has 2 negatives. So in order for this to get positive, the R would originally have to be a negative. So R is going to be negative 1. Again, you can think of it as just the opposite of what you see. And S is going to be 5. And we can confirm this by putting this in Desmos. We can see that our first 0 crosses the x-axis at negative 1. That's our R. And the second 0 crosses the x-axis at 5. That's our S. So that's what that means there. Okay, so let's look at some examples of factored form. Can the expression be factored? If it can, R, and S equal to each other, and state whether they're positive, negative, or 0. Assume that R is less than or equal to S. So the first thing I see is that this graph crosses the x-axis in 2 places. So since it says r is less than or equal to s, I'm going to say that this one furthest to the left is r and this one furthest to the right is s. And we can see, so this is the x-axis, this is x equals 0 right in the middle, and so anything to the right of it is positive and anything to the left of it is negative. And by the way, I want to cover this, these quadrants. Quadrant 1, and I think we talked about this in a previous video, but quadrant 1 is going to be our rightmost quadrant. Quadrant 2 is this one. Quadrant 3 is this one. And quadrant 4 is this one. Just wanted to mention that. Anyway, so first of all, r is going to be negative. So r is negative. It can be factored because it crosses the x-axis. That's what that means. So it can be factored because it crosses the x-axis. R is negative because it's to the left of x equals 0. S, on the other hand, is going to be positive because it's to the right of x equals 0. And they don't equal each other, obviously, because they're two different numbers. One's positive and one's negative. Let's look at another example. Can it be factored? If it can, tell us about r and s. Well, I see it crosses the x-axis in two spots. So r is going to be the smaller one, s will be the bigger one. And they're not equal because they cross in different spots. So they're both positive though. R is positive and s is positive, and also r does not equal s because we have the graph crossing in two separate spots. And they're both positive because they're both to the right of the origin. 0. Can it be factored? Well, actually, and then did we say it could be factored here? Yes, it can be factored because it crosses the x-axis. If it crosses the x-axis, it can be factored. Here, it cannot because it doesn't cross the x-axis. You see, it's floating above it, and it's never going to cross it. So, can't be factored. Which means that we can't say anything about r and s. That's it. That's the end of the story. Can't be factored. What about this guy? Well, it only appears to cross the x-axis in one spot, so that means that our zeros equal each other. Can be factored because there is at least one 0. And they're both positive because they're both, the same number and they're to the right of 0. Alright guys, that is the end of this video. I hope this was helpful for y'all. Thanks for watching, and I'll see you guys next time.